In this video, I want to show you how you can use the central limit theorem and ideas from the normal distribution to solve this problem. The weight of a small package of potato chips is normally distributed with a mean of 1.5 ounces and a standard deviation of 0.1 ounces. Suppose a random sample of 4 bags has a sample mean of 1.4 ounces. Well, let's go ahead and extract some of this information from this problem. First off, we have a population of potato chips that is normally distributed with a mean equal to 1.5 ounces and a population standard deviation equal to 0.1 ounces. Now, again, these are parameters from a population. Then we have a sample of size 4. So n is equal to 4, and a sample mean from that sample equal to 1.54 ounces. If we want to know what the distribution of sample means is, we know by the central limit theorem that even though we have a smaller sample size, because our population is normally distributed, that the distribution of x bars, so our sample means, will also be normally distributed, where our mean will be equal to mu of x bar, which is just simply equal to our population mean of 1.5 ounces. And our standard deviation of our sample mean, so sigma x bar, is equal to sigma over the square root of our sample size. So this is not equal to 0.1 ounces. This is equal to 0.1 ounces divided by our sample size, which in this case is equal to 0.05 ounces. So if we draw the distribution, then we have a mean of 1.5, a standard deviation of 0.05, which means that one standard deviation up will be 1.55, 2 standard deviations up will be 1.6, 3 will be 1.65. Draw our deviations down from the mean, we'll get 1.45, 1.40, and lastly 1.35. Now, if we want to know the probability a random sample of 4 will result in a sample mean of 1.54 ounces or more, so the mean that we actually obtained, that value, and more extreme than that, or greater than that, then we want to know this region. What proportion or probability is it that we would actually obtain a sample mean that big or bigger? Well, we can use the ideas now from the normal distribution. So once we know that x bar is normally distributed, then the way that we solve this problem is no different than any other normal distribution problem. So we want to know the probability that x bar is greater than 1.54 ounces. Well, this is equivalent to saying the probability of z is greater than the z-score of x bar minus its mean divided by its standard deviation, which in this case is equal to 1.54 minus the mean of 1.50, all divided by the standard deviation of not 0.1, but our standard deviation of our sample mean, which is 0.05. So this is then equal to the probability that z is greater than this expression, which is equal to 0.80. And we can look this up on a table, but what we'll find again is that whenever we look up a value from the standard normal table, it'll always give us the area below the standard normal curve. So we don't want that. We want the area above, so we need to subtract whatever we find from the table from 1. So if we go over to the standard normal table, if we look up the z-score of 0.80, we find that value is 0.78814. So that means that this area in here is 0.78814. We want to know this area, so if we take that and subtract it from 1, the total area under the curve, we'll get a value of 0.21186. So that means that the probability that we randomly select a sample that has a sample mean of 1.54 or above is equal to 0.21186.